fundamentally, if we have a set of dimensions, we can think of a given quantity. Okay, now this is going to push some of you. We could think of a given quantity as a pair of a value and some dimension. So it has some number, 3. And then it has, say, units in this case, units associated with it. So it's meters per second, or people per year. And if quantities, dimensions, or units, either one of them, could be represented as products of power, okay? So you might have rate of water flow as liters cubed per unit time. So it might be liters cubed per second, the rate of the Saskatchewan River flowing. Or we could measure it in gallons per year. We could do that too. Those are just different units for measuring something of length to the cube per unit time. This is the dimension. We have different ways of measuring it. Liters per second, gallons per year. Right? And so we have a number. We have a number, 3. And maybe it means 3 animals, or maybe it means 3 thousands of animals in our model. And that's kind of metadata about that number, okay? We could also think of it as kind of a vector in a d-dimensional space where each dimension represents an exponent for a particular dimension. You notice here, this is like liters per unit time. That's the, this says liters cubed per unit time, or sort of length cubed per unit, not liters cubed. What am I saying? Length cubed per unit time, and it might be cubic meters per unit time. Sorry, I shouldn't have said liters. It's cubic meters per unit time. So whatever a measure of length is, maybe it's cubic meters, maybe it's cubic feet. We can have different units of measuring the same dimensional quantity. Okay, different units of measuring rates of water flow. And it turns out that the fact that we have these pairings of a value and a dimension constrains what we can do meaningfully with them. So, for example, we might express